Now let's revisit a previous discussion that we had. We talked before in a different video, I say we, but it was me, wasn't it, about partial sums. So we're going to revisit that. Since S sub n is a partial sum, it leaves out terms. And in fact, it leaves out the terms a sub n plus 1, a sub n plus 2, and all the ones after that, because if we're talking about S sub n, we're only adding the first n terms. I think for this, just kind of a little bit of a visual is in order. S, the entire sum, would be a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n minus 1, we'll say, plus a sub n plus a sub n plus 1 plus a sub n plus 2. How long is this going to go on? It's done now. Plus dot dot dot. The whole sum is all of these, right? And I'm putting an arrow saying that we're adding all of the a sub 1, a sub 2 that we just wrote down, and then it keeps going on to infinity. S sub n is a part of that sum, and it leaves out all of the terms from a sub n plus 1 on. So the sum S is S sub n that we added together plus a remainder. And we're going to say that this is R sub n. I'm just going to point out what I did with the colors here. You see the partial sum is S sub n, and I've got that in yellow. And then the remainder is red, and yellow and red make orange, which is the whole sum. Anyway, we can then say that in this way, or thus, S sub n is an estimate of the sum S, and the remainder is R sub n is equal to S minus S sub n. And that's what we would get in this equation using the symbols. S equals S sub n plus R sub n if we subtracted and solved for R sub n. And as you can see here, R sub n is equal to a sub n plus 1 plus a sub n plus 2 plus all the rest of them. If f is decreasing, as is the assumption for using the integral test, then the following picture applies. Here I have the graph of a decreasing function and then some values on the x-axis, n, n plus 1, n plus 2, n plus 3, of course equally spaced out. And in fact, let's go ahead and point out now that the width between n and n plus 1 is 1. We're going to form a series of rectangles. And I'm going to use right endpoints of each interval to give me the height of a rectangle. Now I made some of these blue rectangles here. And for the first one here with the left bottom endpoint at n, the right bottom endpoint at n plus 1, we can see that the height of that rectangle is f of n plus 1, which we're going to think of as a sub n plus 1. Therefore, the area of the first blue rectangle is a sub n plus 1. Likewise, the height of the second rectangle is a sub n plus 2, and since it has a width of 1, its area is a sub n plus 2, and the third has an area of a sub n plus 3. We have, and then so on, right? These would continue on. So we have an expression for the remainder that says the remainder is a sub n plus 1 plus a sub n plus 2, and so on. Therefore, we can say that the remainder sub n is equal to a sub n plus 1 plus a sub n plus 2 plus dot dot dot, and so on. And you can see from the picture that since I'm using right endpoints, all these rectangles added together are going to be less than the integral that would start at n equals 1. So the remainder is less than or equal to the integral from 1 to infinity of f of x dx. If we turn this around though and start using left endpoints, then I can create this series of pink rectangles, the first one of which has the left endpoint of the subinterval at n plus 1. Therefore, its height is a sub n plus 1. The area of the first pink rectangle is a sub n plus 1. The second is going to be a sub n plus 2, and that's going to be and so on. So we can then say that the remainder sub n, which is, well, as we already knew, a sub n plus 1 plus a sub n plus 2, and so on, is, now look, these pink rectangles are above the function because we're using a left endpoint for a decreasing function. Therefore, all of these are greater than or equal to the integral. I am stopping mid-sentence because I just realized I had a mistake in the blue one. Folks, I meant to write down that this integral started from n and went to infinity. So let me fix the blue one. So just to recap, r sub n is less than or equal to the integral from n to infinity of f of x dx. All right, cool. Looking at the pink rectangles, we're starting that integral from n plus 1, right? That's the leftmost endpoint for that rectangle, that first pink one. And the sum of all the pink rectangles is bigger than the integral for the function, but starting at n plus 1. Therefore, r sub n is greater than or equal to the integral from n plus 1 to infinity of f of x dx. From these two inequalities, we can estimate the error in finding a partial sum. Formally, we'll say, suppose f of k is equal to a sub k, where f is a continuous positive decreasing function for x greater than or equal to n, and the sum of a sub n is convergent. If the remainder sub n is equal to s minus s sub n, as we already saw, then that remainder sub n is between the blue integral and the pink integral. In other words, the remainder is bigger than the integral from n plus 1 to infinity of f of x dx, and smaller than or equal to or less than or equal to the integral from n to infinity of f of x dx. I don't know where that plus came from. Since r sub n is represented by s minus s sub n, we can say s minus s sub n is then between these two integrals, which means that the sum itself, and this is what we were after, if we add s sub n to both sides, is between s sub n plus the pink integral from n plus 1 to infinity of f of x dx and s sub n plus the blue integral from n to infinity of f of x dx. And it looks like we're writing the same thing all over the place, but notice that the pink integral starts at n plus 1, the blue integral starts at n, and what we're saying is the actual sum is sandwiched between the partial sum plus the pink integral from n plus 1 to infinity and the partial sum plus the blue integral, which is from n to infinity. We can express this using some vocabulary. The partial sum s sub n plus the integral from n plus 1 to infinity of f of x dx is called a lower bound for the sum s. And the partial sum s sub n plus the integral from n to infinity of f of x dx is called an upper bound for the sum. It allows us to narrow down, hey, the sum is between two numbers. And if we want to increase the accuracy and tighten up the interval, then we would increase n, of course.